Welcome to this lecture in the ongoing series of lectures in real analysis. We'll be continuing our discussion on infinite series. This will be a short lecture and we'll discuss some algebraic properties of convergence of series. So let us recap what we did the last time. Given a sequence of real numbers, we can associate to it a corresponding infinite series, which is just this symbol and nothing more. Once we have such a thing, this thing is called an infinite series, and once we have such a thing, we can define the nth partial sum of it by declaring Sn as the sum of the first n terms, and the sequence, this sequence is an important sequence. Alright, so we say that the series sigma an is convergent if this sequence of nth partial sums converges, and if this happens, if the sequence of nth partial sums converges, then we write this equation where it just means that, it means what it means, but one thing I want to mention, which I did not mention the last time, is that once we are able to write this, meaning the sequence of nth partial sum converges, then this number is called the sum of the series. It's just a terminology, and it's a good terminology. All right, and we saw that this geometric series converges if the absolute value of a is at most, or rather strictly less than 1, and the sum is equal to this number. And we saw that this series, this is called the harmonic series. I should mention that this is the harmonic series. So this diverges. We saw a proof of it. All right, and lastly we saw the Cauchy criterion of convergence, and this is it. You can read it if you want to. You can just pause the video, and that's that. So these are the problems, just two very simple problems. And now we quickly finish what we want to do. So suppose we are given to convergent series, then we claim that the series formed by adding term-wise the elements of the two particular series is also convergent, and the scale of the first series, or well, any of those series, is also convergent. And this is very simple. So all we do is let Sn and Tn be the sequences of partial sums of the two series. I'm being brief. I am not decorating these with limits. Maybe I'll just put a subscript of these respectively. Then it's just, then note that the nth partial sum of this guy is Sn plus Tn, and since the sequences Sn and Tn converge individually, this particular sequence also converges, and in fact what we see is that the sum of this series is that. So this is the limit of Sn and that is the limit of Tn, and we can write this. So in fact the theorem can be upgraded to mention that this is equal to, provided we understand what it means. Okay, and I'll leave the second one as an exercise. It's much simpler. It's, well, there is nothing complicated here, so I would say it's even simpler than the first one. Alright, so just a very not at all surprising fact. And then let us consider one more concept, and that's it. So we have a series, and suppose we pick a sequence of natural numbers. It's strictly increasing. Then we can define, let's say we define b1 or not let's say, we define b1 as the sum of the first n1 terms, then we define b2 as the sum of the, you know, the terms corresponding to this interval. So you 1 to n1 we have assimilated here, then the things, the indices corresponding to this interval we have assimilated here, and so on. So it's kind of, we have just clubbed things from the series in some packets, and we have formed a new sequence, and therefore hence we have given rise to a new series. So this thing, the series that is formed out of these BIs is called a regrouping of the original series. For this terminology is self-explanatory, so nothing to be said about that. And the very simple theorem is that if we have a convergent series, then every regrouping of the series is also convergent with the same sum. And here is the proof. I will not do it purely formally, but I will write one line. Is it that observe that the sequence of partial sums of any regrouping of the convergent series is a subsequence of the sequence of partial sums of the series itself. So the sequence of partial sums of the regrouping of any regrouping is a subsequence of the sequence of partial sums of the parent convergent series. And since the series is assumed to be convergent, this sequence of partial sums is convergent, and hence any subsequence of it also is convergent, and it in fact converges to the same limit. And not just that any regrouping is convergent, we also have that it is convergent with the same sum. So that's it. It's a very simple fact. And I guess that's it for this lecture. So not much. As usual, like, comment, share, subscribe. Thank you for listening, and I'll see you next time.